Okay, so resonance structures are a 2D representation of a molecule that exists in multiple states or multiple arrangements, I'll say that. And that's not necessarily your book definition, that's just kind of my definition. Okay, multiple arrangements. Okay, and so it's a Lewis structure, but taking it a step further. So a resonance structure occurs most of the time when a molecule is non-symmetric. Symmetric have two M's, you think?
Yeah.
Okay, good. Okay, non-symmetric. Okay, and usually, or most of the time, right, it's when there is a double bond. Okay, so resonance structures occur when there's a double bond and it's non-symmetric. That's usually when resonance structures occur. When we say multiple arrangements, that doesn't mean that the atoms necessarily are moving. It means that the electrons are moving. They're relocating. Are they being in a lone pair, or are they going to exist in a bond, or what are they going to do? That's kind of what a resonance structure is, okay? So it's not that our atoms are moving around space necessarily. It's that our electrons can be either in a bond or in a lone pair, and it can exist both ways. That's kind of what we're talking about here. Okay, so we're going to just start in with a couple examples because that's kind of the easiest way. We don't have to follow any necessarily special rules about it like we did with Lewis structures. You still build your Lewis structure the same way, and then now you build more than one. Okay, that's pretty much it. All right, so we're going to look first at carbonate. Can anybody tell me what carbonate is? CO3, negative 2. Good. CO3, negative 2. So we'll draw our Lewis structure just like normal. Okay, carbon gives 4 valence electrons. Each oxygen gives us 6, so that's 18. And then what do we do with this negative 2? We add 2, which means we need a total of 24 electrons. Okay? We agree so far? Yep. All right, so in our Lewis structure, which needs to be our central atom here? Carbon. Okay, and then we would go oxygen, oxygen. And we start with a single bond to each. Okay, which means we've used 4. We've got 20 left. Okay? Yeah, sorry. My bad. So we've used 6, not 4. That's my fault. All right, here we go. Now we're moving. So we've got 18 left. If we go 2, 4, 6, 8, 10, 12, 14, 16, 18, right? We've used all our electrons, but what's the problem? Carbon only has 6. It's got a sad face, right? So that doesn't work. Okay? So how can we fix that? How can we complete carbon's octet without adding or taking away electrons? We can throw one of these lone pairs into a double bond, right? All right, so I'm going to take away my lone pair, and I'm going to put it into a double bond. So now we've got a complete octet, a complete octet, a complete octet, and a complete octet. We've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, which is what we should have used. Are we good so right there so far? Mm-hmm. Okay, so now this is where the resonance structures part comes in. How did we decide which oxygen we take the lone pair from and put it into the double bond?
Randomly did it.
Yeah, we just randomly picked one. Does it matter which one we do it? Which one we take the double bond from?
No.
It doesn't matter. But here's the thing. Carbonate can exist with any of those oxygens carrying the double bond. So we have to draw it all 3 ways, right? We have to draw it showing all 3 of those possibilities. So what we do to indicate that a resonance structure is being drawn is that we draw a double-headed arrow to show that these two structures are the same. Okay? And I draw the same thing, except now my double bond might be on this oxygen, right? Instead of the one on the right. Okay? Everything else looks the same. Okay, so now I've covered two of the oxygens with a double bond. But can't the one on the bottom have a double bond too? Right, so we draw the third resonance structure. Okay, so when we draw resonance structures, it's really, really important that we include that double-headed arrow. That tells us that these two structures are the same thing. There's no change that's happening here. The only thing that's changing is the placement of the electrons. Okay? There's one last part that has to go onto a resonance structure. Okay, and it specifically has to come onto the resonance structure when we have a charge, and that's that we need a set of brackets. Okay, and we put the charge on the outside of those brackets. Okay, let me make it a little smaller so we can really see what's happening here. Okay, when there's a charge on the resonance structure, we draw brackets and we put the charge on the outside. So what that's telling us is that distributed within these structures, there is a -2 charge, right? In this molecule, I'm going to show you where the charge comes from a little bit, okay? And if this makes you a little uncomfortable, like that's okay, but I'm going to show you what is happening and where the charge comes from, okay? So, in this molecule, how many valence electrons does each oxygen contribute? 6. Each oxygen contributes 6. And around this oxygen, there are 1, 2, 3, 4, 5, 6 electrons. Agreed? So it's pretty happy, right? It gave 6. It's got 6 around it. We're good to go. Carbon gave 4, right? So hits 4 are 1, 2, 3, 4, right? The other oxygen gave 6. 1, 2, 3, 4, 5, 6, right? But it's got another one right here. So this oxygen is carrying one of the negative charges, okay? Then our last oxygen has 1, 2, 3, 4, 5, 6, 7. It's carrying the other -1 charge. So that's where we get the -2 charge from out of carbonate. Does that kind of make sense? It's got more than what it contributed, so that's where that charge is kind of hanging out there, right? If we looked at where our electrons were located, this oxygen has an extra, and this one has an extra, so that's where our negative charges are hanging out. You do not have to label that. I'm just telling you so that you have a little bit more of an idea of the real structure behind it. You have to have the brackets with the -2, because that tells us within these structures, there's an extra 2 electrons somewhere. Okay? Questions? All right, let's try another one. Anyone recognize this polyatomic ion? Oxalate. Oxalate, good. Okay, so C, each carbon is giving 4, which is 8 plus 24 plus 2. So we need 34 electrons, I think, if I counted right. Would we agree? Okay. 34 electrons. I've got double carbon, so that means I probably am going to have what? 2 central atoms. Could have a double bond, but I'm going to have probably 2 central atoms. So I'm going to go carbon, carbon, oxygen, 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 oxygen. Right? So here's 1 or 2, 4, 6, 8, 10. Right? I've used 10, which leaves me with 24. All right, so here's where we got to do some thinking. Right, if we drop lone pairs around each oxygen, If we drop lone pairs around each oxygen, that's how many? 24 electrons. Right? So that leaves us with enough, but what's the problem?
Carbon only bonds twice.
Our carbons don't have complete octets, right? Our oxygens each have complete octets, but our carbons do not. So what can we do?
You could add a double bond in the middle.
These 5 bonds right here. All the bonds. Right? Those are your 2 electrons. Okay, so I'm going to take a lone pair from what? Where do I take a lone pair from? And oxygen, right? It doesn't matter which one. So let's take a lone pair, and we're going to bump it into a double bond here. Okay, so I've taken a lone pair, I bumped it to a double bond. Now let's see, I have a complete octet. Yep. What about this carbon? No good, right? So what can I do also on the other side? Take another one. So it doesn't really matter. I could use this one and take it to a double bond. I could use one of the ones from the other one. It doesn't make a difference. Okay, so now I've double bonded here, which means now I have a complete octet for carbon. So what's the issue now? There could be another way to draw it, right? We've got 2 double bonds and 2 other oxygens, so we need to draw another structure. So we draw the double-headed arrow. It doesn't matter what order our resonance structures go in. We just have to hit all of the combinations. Oh, I might have already done them all. Oh, no, I didn't. So there's 4 different structures we have here. Okay? One with both our double bonds on the top, one with them diagonal to the right, one of them diagonal to the left, and one of them with both our double bonds on the bottom. Sorry, I'll move this guy over here so you can see him. I had 4. Did you have more than that? So if we do a double bond, yeah, I see what you're saying, but I'll show you. If we do a double bond that looks like this, then carbon has too many, right? So they still got to be on opposite carbons, okay? So we still got to make sure all of our octets are complete. So I had 4 structures, and I didn't draw all the outer electrons. You still would need to do that, but for time-saving purposes, I didn't do that on the board, okay? You would still need to have all of your outer electrons filled, okay? So we're still got to be adding electrons here. Yeah, did you have a question?
I can tell which one I'm missing.
Okay. So do you have them both double bonds on the top? Right, like this one? Both double bonds on the top.
Yes.
Okay, and then we have diagonal to the right are our double bonds.
Well, I did them like up and down.
Oh, okay, that's fine. All right, so let's look. Missing on here the brackets with my -2 charge. If there is no charge on your resonance structure, you don't have to draw the brackets. Okay, the brackets are only if there is a charge distributed somewhere throughout that structure. Okay, that's also something that we should point out for regular Lewis structures, is that if I have a regular Lewis structure, I also would want to go ahead and put brackets around it and put a charge on the outside. Okay, we didn't talk about that a whole lot with single Lewis structures, but that's a good habit to probably get into. Okay, any questions? All right, that's where we're going to stop with notes for today.